Kia ora and welcome to video 21 in the series Insightful Integration. This video and the next one, the integrals involved are quite intense. There we go, just throw it onto the screen and freak you all out. This problem involves a reflective property, and the hint there is that those two integrals are the same. So if we can use this hint to simplify this integral and then see how it relates to the problem we're trying to find, the question is actually quite a simple question. So as always, give it a go and we'll catch you afterwards for the solution. Okay, first up, before we look at the specific integral, which looks messy, we're going to look at this reflective property in a bit more depth and prove it. Because I guess when you're given a hint in a question, which actually makes the question a lot easier, it is quite nice to know where that hint came from and how it was useful. So in this case, I've thought about a diagram that we could look at to prove this. We're also going to look at it from a calculus perspective. So if I just make any random function here on GeoGebra, and I can use a freehand shape. So I'm going to make something that looks kind of like a cubic, but it doesn't have to be a cubic, any function. And suppose I want to find the integral between 2 and 5. Now in this case the integral would be also the area below the curve, because the curve doesn't have any roots there, but this method also works if your function goes through the x-axis. It works in general. So I've got my function f of x there with limits of 2 and 5 for the lower and upper limits of the integration I'm trying to achieve. If I shift that graph to the left by 7, because the lower limit is 2 and the upper limit is 5, then I'm going to get f of x plus 7. So if I first up just do that, f of x plus 7 in there. Okay, what I've done, if I just find that curve, I've shifted the graph just to the left by 7, and I'm taking the limits of 2 and 5, added those together. That's the f of a plus b part. So what you can see is that the 2, when I moved it left 7, ended up being over at -5, and the 5, when I moved it over, became -2. So that's f of x plus 7. Now if I was to then say, well, what does f of 7 minus x look like? Because that's the minus part in this translation reflection kind of formula. Well, for that, let's have a look at that. F of 7 minus x. Okay, that reflects the curve back in the y-axis. So whenever you change an x to a minus x in a function, it just treats all the x values that were positive as negative ones and all the negative ones as positive ones, so hence a reflection. And now if we look back at the original area we're trying to find, which was between 2 and 5, it went over to -5 and -2. It's now been reflected back to between 2 and 5, but the difference is that the lower limit of 2, the function was, let's just try and highlight that, was there, and now that lower limit appears at 5 there, and then the higher limit, the upper limit of 5, which was there, is now appearing at 2. Okay, but what you need to do is convince yourself that that area between 2 and 5 is exactly the same as the area between 2 and 5 on the purple curve. It's just flipped around. So if I was to put one last thing, if I was to show that reflection by going x equals 3.5 in, because 3.5 is halfway between 2 and 5, and then I take my original function and reflect it about that line. So my original function was the black function. If I then reflect it about the line, I get the purple function. Okay, so what that's telling us is if we take f of x, if we want to find the integral between a and b, we can shift it to the left by a plus b, reflect it back so it's a plus b minus x, and the area will be the same. Okay, a more algebraic proof using calculus is actually very straightforward. If we take the integral between a and b of some function f of x, well, that's just going to be f of b minus f of a. Notice I've used capital letters for the antiderivative. So you say where f dash is equal to f. Okay, now if I was to do the other one, the right hand side, integral between the same limits of f of a plus b minus x, that's a linear transformation in there. Wherever there's an x, it's been replaced by a plus b minus x. Okay, so the inner function is a linear function. So when I anti-differentiate it, I'm going to get capital F of a plus b minus x divided by negative 1, and then I'm going to have to evaluate the limits between b and a. That's similar to something like, if I anti-diffed cosine of x, I get sine of x. If I anti-diff cosine of, say, 3 plus x, I'd just get sine of 3 plus x. But if it's 3 minus x, it's not just sine 3 minus x, I'd have to divide by negative 1, the derivative of the inner function. And that works for linear functions, when the inner function's a linear function. Okay, so then I sub in my limits. My first limit is the upper limit b. So if I sub that in, I've got f of a plus b minus b, which is f of a, divided by negative 1. And then I always minus. The next limit is a, so f of a plus b, I just sounded like I swore at you guys, I'm so sorry. A plus b minus a is f of b divided by negative 1. And then you can see there that becomes f of b minus f of a as before. Okay, so this reflective property works. And now we just need to go, well, why does that help in this particular function? Okay, so we're integrating between 2 and 4, some ugly integral there. That top thing does simplify. The 6 minus x written in brackets there is just to kind of suggest to you what the substitution needs to be. But we're going to use that because we've got the hint there to tell us that anyways. So a plus b minus x is 6 minus x. And it's saying wherever there's an x, we're going to replace it with a 6 minus x. Hopefully that makes sense. So I'm going to do that. I'll keep the same limits 2 and 4. That numerator becomes log of 9 minus 6 minus x, 9 minus 6 minus 6 minus x. That was really, really tedious. Okay, but we're saying wherever we get an x, we're replacing it with a, I'm not going to put equals, we're going to replace it with a 6 minus x. That's the same as seeing a 6 minus x and replacing it with an x, right? So I didn't need all of those extra brackets. I could quite simply have just got rid of the 6 minus x bit and just made it x. Okay, you would have got that if you'd simplified. And then on the bottom, the 9 minus x one, the bottom left one, if I make x 6 minus x, I'm going to get 3 plus x there. So ln of 3 plus x. And then the other one, if I replace the x with a 6 minus x, I'm going to get ln of 9 minus x. Okay, and apparently those integrals there are equal. Well, they've got the same denominator, and the numerators, that one there is 3 plus x. The numerators are similar in the sense that they both appear in the denominator. So this is a common problem with integrals. If you can prove that two integrals are the same, which we've used this reflective property to do so, then adding the integrals would mean we have 2 times the original one. So like if we called this I, this is also I, then adding them, we get 2i. 2i is equal to the sum of those integrals. Now when we take two integrals and add them, it's the same as integrating the sum of them. So we end up integrating ln of 3 plus x square rooted plus ln of 9 minus x square rooted all over the same thing. Because they've got common denominators, when I add them I can put those fractions together, and that's the point of this question, is that we're actually just integrating 1. How cool is that? 2i equals the integral between 2 and 4 of 1 dx. Now of course 1 integrates to x between 4 and 2. 4 minus 2 is 2. So our integral that we started with, the definite integral, the answer is equal to 1. A really neat problem. The reflective property obviously made that a lot simpler, and often that is the case when a problem looks really, really nasty. It's probably a lot easier than it looks. I'm reminded about one in last year's scholarship exam that asked to integrate something like tan of 1 times tan of 2 times all the way down to tan of 90. No, actually it wasn't tan of 90 because that's not defined, it was tan of 89. And it looked horrendous, but when you paired up all of the expressions, tan of 1 and tan of 89 goes with tan of 2 and tan of 88 and so on. If you pair those all up, you ended up integrating 1 in that as well. There's often a trick.